Hello everyone. So in this video of chemical thermodynamics, I'll be talking about enthalpy changes in thermochemistry. So thermochemistry deals with enthalpy changes in chemical reaction. So the first enthalpy is the enthalpy of chemical reaction denoted by delta RH. Now let's consider this equation, and this equation is A plus B giving you C plus D having stoichiometric coefficients A, B, C and D respectively. We can say enthalpy change of a chemical reaction is the difference between the sum of the enthalpies of the products and that of reactants with each substance is definite in physical state and in their moles, and it should be represented by the balanced chemical equation in a reaction or of a reaction. So delta RH is equal to summation of enthalpies of the products minus summation of enthalpy of the reactants. Now next, exothermic and endothermic reaction. The enthalpy of reaction can be positive or can be negative depending upon enthalpy of products or enthalpy of reactants. If enthalpy of product is greater than enthalpy of reactant, so delta RH is positive. That means the reaction is endothermic. If enthalpy of product is lesser than the enthalpy of reactant, that means delta RH is negative, and here heat is released and the reaction is exothermic. Now standard enthalpy of reaction, which is delta RH naught. To compare enthalpy changes of different reactions, they have to be reported under similar set of conditions. And what are thermodynamic standard state? The standard state of a substance is the form in which the substance is most stable at 1 atmospheric pressure or 1 bar pressure and at 298 Kelvin temperature. If the reaction involves species in solution, in standard state or in solution state, it should be having 1 molar concentration. Standard state of certain elements and compounds are like hydrogen should be in gaseous, mercury in sodium is in solid state, graphite solid, ethanol should be in liquid, calcium carbonate in solid, and water liquid, carbon dioxide in gaseous. Refer to 1 bar and 25 degrees Celsius temperature. The standard enthalpy delta RH naught of reaction is the enthalpy change accompanying the reaction when the reactants and products involved in their standard state. Now, thermochemical equation. It is the balanced chemical reaction or balanced chemical equation in which enthalpy change, physical state and the number of molecules or number of moles of reactant and product have been specified. Equation should be properly balanced. The number of atoms will be equal on left hand side and right hand side. The values and appropriate sign of enthalpy change should be given on right hand side, and the physical state of reactant and product should be specified by letter like solid by S, liquid by L, gaseous by G, aqueous by AQ. And next should be the given value of delta RH naught assumes that the reaction occurs at the in the given direction. Delta RH naught for a reverse reaction equal in magnitude and opposite in the sign that of forward reaction, and exothermic reaction on reversal becomes endothermic and vice versa. And when the coefficient indicating the number of moles of all the substances in thermochemical equation are multiplied or divided by certain numerical factor, that corresponding delta RH naught need to be multiplied or divided by the same. Like the example here, methane is burned to give you carbon dioxide and water. Here standard enthalpy of reaction would be minus 890 kilojoule. Equation is balanced, physical states are mentioned, and delta RH value is mentioned on right hand side along with the products. Now next is standard enthalpy of formation. Standard enthalpy of formation of a compound is the enthalpy change that accompanies a reaction in which 1 mole of pure compound in its standard state is formed from its element in their standard state. For example, the formation of 1 mole of methane in its standard state from its reactant by carbon and hydrogen in their standard state. It could be represented as carbon as a graphite it is taken, hydrogen in a gaseous state it is taken, and they are forming methane which is gaseous, and here delta RH naught is minus 74.8 kilojoule. Here delta FH naught of methane is minus 74.8 kilojoule per mole. Now standard enthalpy of reaction from standard enthalpies of formation. Standard enthalpies of formation of compound is used to determine standard enthalpies of reaction. Calculation of delta RH naught from delta FH naught of compounds are based on: number 1, standard enthalpies of formation of element is always 0. That means enthalpy of hydrogen, chlorine, carbon is always remain 0, and standard enthalpy of formation of a compound is equal to its standard enthalpy. That means standard enthalpy of formation of a compound is equal to its H naught value. Consider this is one reaction and standard enthalpy of reaction need to be calculated. That means delta FH naught need to be calculated. What I am going to do, I will take C's enthalpy plus D's enthalpy minus A's enthalpy plus B's enthalpy. Alright, and I will be getting value delta F H naught. Do not forget taking their coefficient along with their enthalpy. Now standard enthalpy of combustion, that is delta CH naught. The standard enthalpy of combustion of a substance is the standard enthalpy change accompanying the reaction where 1 mole of substance is in its standard state is completely oxidized. For example, in this reaction ethane is getting oxidized to give you carbon dioxide and water molecule. Here standard enthalpy of combustion would be minus 1300 kilojoule. Now bond enthalpy. Now consider this reaction. Here hydrogen molecule is converting into hydrogen atom. So here delta RH naught value is 436 kilojoule. It shows that hydrogen bond in 1 mole of molecule from hydrogen is decomposed to produce hydrogen atoms. So the enthalpy change of the reaction is 436.4 kilojoule, and the enthalpy change required to break the particular covalent bond of 1 mole of gaseous molecule to produce gaseous atom or radical is called bond enthalpy. Now average bond enthalpy in polyatomic molecules. Each covalent bond in polyatomic molecule is associated with its own specific bond enthalpy. The thermochemical equation of dissociation of water molecule is dissociating from its gaseous state to produce 2 hydrogen atoms and 1 oxygen atom, and this is the enthalpy which value is 927 kilojoule. The above equation implies that the enthalpy change of breaking of 2 OH bond in 1 mole of gaseous H2O molecule is 927 kilojoule. How the bond are breaking? Let's see here. In first step, H2O gaseous will be converted into OH, which is gaseous, plus hydrogen atom, and this much energy is the enthalpy change. In second step, the bond between oxygen and hydrogen would be breaking to give you oxygen and hydrogen atom. Delta RH naught value would be this, and on adding these two, we will be getting water is breaking into hydrogen atom and oxygen atom, and all are in gaseous state, and total enthalpy change will be 927 kilojoule. For polyatomic molecules, the average bond enthalpy of particular bond would be considered. Thus, average bond enthalpy of OH bond would be 972.2 is equal to 463.5 kilojoule, or delta H naught of OH would be 463.1.5 kilojoule per mole. Reactions and bond enthalpies. In a chemical reactions, bonds are broken and formed. The enthalpies of reaction involving substances having covalent bonds are calculated by knowing the bond enthalpies of reactants and those of products. The calculation assumes all the bonds of given type are identical. Suppose enthalpy change of reaction need to be calculated, so delta R H naught would be equal to summation of enthalpy of reactants minus summation of enthalpy of product. Consider this reaction where this HI is going to be formed in gaseous state by the standard state of hydrogen and iodine. Both are taken in gaseous state. So delta H naught would be calculated as delta H naught of hydrogen and hydrogen. This bond would be broken, plus delta H naught of I and I. This bond will be broken, minus 2 multiplied by Y2. I have taken stoichiometric of HI, multiply by delta H naught of HI. In this way, enthalpy change of reaction would be calculated. Thank you.